This is Chapter 12, Earthquakes, Lecture 2. We'll pick up with a major earthquake in a subduction zone, and that was the Tohoku, Japan earthquake in 2011. We'll say that was a huge earthquake. So 9.0. That was in the subduction zone beneath Japan. It occurred where the Pacific plate is subducted beneath Asia, and the earthquake displaced the seafloor, which resulted in a huge tsunami that swept inland many kilometers. It destroyed entire towns, and of course, the Fukushima nuclear reactor, which had a core meltdown due to the failure of coolant pumps and backup generators. And then the earthquake also caused destruction on land from ground shaking. So, just absolutely devastating. And then the Haiti 2010 earthquake, that's a magnitude 7 earthquake located on strike slip faults near the capital city of Port-au-Prince. We had just an enormous number of people lost their lives from that, mostly due to the collapse of the buildings in this country. New Zealand had a similar sized earthquake. It's very hard for me to compare, one earthquake on one side of the planet to another, but it is said that due to the construction of buildings in this area, there were no deaths and minor damage as well. There was also a magnitude 6.3 earthquake in 2011. It was smaller and it killed 200 people in the area. It was located closer to the city, and the buildings there had already been damaged in 2010. So they were at risk because of that. So, more on tsunamis and how they form. I've said it previously, but tsunamis occur when the seafloor is faulted and uplifted, as happened during the 2004 tsunami in Sumatra. And the seafloor above the overriding plate flexes or bulges to accommodate the forces of convergence. This is only one way, of course. Anytime you could have a landslide displacing seawater, for instance, but in this case, this is fault movement induced tsunami. Um, and when the rupture occurs, the bulging plate changes shape catastrophically. Water above the plate responds by lifting up from the ocean bottom, and that forms a ridge of higher water. And then this large wave and then accompanying wave troughs causes the ocean to retreat and withdraw from the shoreline, which is a big warning sign that a tsunami might be coming soon. And they saw that in Indonesia. If that happens, you want to get out of there fast. Tsunamis radiate away from the disturbance, and they can travel between 600 to 800 kilometers per hour. In deep water, that wave can only or may only be a meter or so high, but as it approaches the shoreline, you have a lot of friction increasing, and the energy concentrates and becomes a massive wave. So, how else does a tsunami form? Underwater landslides, those will displace water. Volcanic eruptions, you have catastrophic volcanic eruptions removing land, which allows ocean water to rush in. All right, so like Krakatoa was an issue. There they had not only volcanism but also a tsunami associated with that collapse. All right, another slide, kind of like the Sumatra slide we had at the beginning of this chapter. This is Chile, 1960. A tsunami swept out across the Pacific Ocean at about 670 kilometers per hour. Each stripe that you see is 2 hours of travel time. And then in Hawaii, same year, same tsunami, it was hit by the Chilean earthquake tsunami 15 hours later. Actually, 61 people lost their lives. And then beyond that, it continued to travel to Japan. So several hours later, 140 people in Japan lost their lives because of this. And just another event, tsunami event in Japan in 1993. That was a major event. 100 people lost their lives in that. New Guinea in 1998. This earthquake actually generated 3 tsunamis that killed 2,200 people. It's no joke. It's very serious, very dangerous. All right. So, how do geologists study earthquakes in the field? Well, after an earthquake's happened, a geologist can measure the offset of features such as faults, fault scarps, see how the distance has changed between different sides, to look at evidence of past movement. They can also document changes in topography through surveying. They could also dig a trench to study the history of fault ruptures and maybe look at something like this. The objective is to try to determine displacement along a fault system by matching parts of the same rock unit on opposite sides of a fault. So I can kind of do that here. Match these two up. They were once together, now they're apart. Something happened. We can also study faults with satellites. All right, so changes in topography that occurred during an earthquake can be measured using satellite mapping techniques. And then after an earthquake, a measurement is made and compared to a previous measurement. Then the two measurements are combined so that the differences are shown as the colored bands in the image on the top left here, which indicates a strike slip movement. And more on trenches dug across a fault. So this is an example from the Anatolian fault system. There was a large earthquake on this system in 1999, 7.4 magnitude. It led to a study to see how much and how often the fault had moved in the past. And in this case, trenches were dug across the fault, and geologists mapped the exposed offset sedimentary beds in the trench walls. They actually looked at layers that contain charcoal, and they dated them using carbon-14 radiometric dating. And from that, they kind of got a timeline for fault movement. They then concluded that a major earthquake occurs on this fault about every 200 to 300 years. It's impossible to predict things exactly, but you can map trends and see, okay, that's kind of what's going on here over time. And then the San Andreas Fault, there's a lot to study here in California. It could be, or it has been, investigated at depth by means of a borehole drilled across the fault. And the borehole is filled with geophysical instruments that collect data on earthquakes as they occur. So you get studies that way in the subsurface. The borehole actually crosses the fault at 3.2 kilometers, about 2 miles below the Earth's surface. So again, what areas are most likely to experience earthquakes? At this point, it's kind of a review, but we're looking at the entire planet here. And we know that we're going to see them along plate boundaries, along old fault systems within continents, and perhaps associated with hotspots, right? We can call these messy collision zones because there's a lot going on here in the continent. Continental rifts also, you'll have movement through earth materials. That's what we can expect. So focusing on the United States. We have a map here showing earthquake hazard. The colors and values reflect ground acceleration here, and the red zones are the highest hazards. Again, this is the New Madrid area near Missouri and South Carolina, which a lot of people who live here don't even know, how at risk those areas are for earthquakes. In the western U.S., of course, the San Andreas Fault is a risky place to live. The Intermountain Seismic Belt from Utah through the Yellowstone region is pretty active. And the Cascade Subduction Zone as well. And these areas have moderate sized earthquakes due to movement on these old faults. Focusing in on Alaska and Hawaii, southern Alaska is located along a subduction zone, so it's extremely seismically active. And then the big island of Hawaii sits over a hot spot, so plenty of potential for energy transfer through Earth materials. Okay. Earthquake forecasting is important. I've said we can't predict exactly when earthquakes will happen, but we can look at the trends of data over time. So this top graph indicates earthquakes that happened along the San Andreas Fault over time. We can identify gaps like the San Francisco gap here, the Loma Prieta gap, the Parkfield gap, when things weren't really happening that much. So the top cross section was made before October 1989, and then we had those 3 relatively inactive stretches. 2 of the 3 stretches experienced major earthquakes, leaving only the San Francisco stretch still inactive. And the question is, when will this San Francisco gap be filled? When will we see more seismic activity there? Okay, so looking at the San Andreas Fault system, the USGS assigned probability to each main fault in the San Francisco area, probability of magnitude of 6.7 or greater earthquakes before 2032. That's coming up. What's the probability? The combined probability of a major earthquake before 2032 on these is over 60%, and there's a 90% probability of a magnitude 6.7 or greater earthquake in the next 30 years in California. So it's very likely to happen. So you can see probabilities increased in these fault lines here, a little less here. And I will say tsunamis aren't out of the question here, but because these are transform faults, they are not rupturing in an upward motion, like in a convergent situation, and displacing a ton of seawater. So the probability for a large, say, tsunami associated with these earthquakes is just not the same as it would be in a convergent zone. Okay. So short-term earthquake prediction. We have lasers that can actually monitor movement along a fault if we know it's an area of concern. And we do, right? So this is still the San Andreas Fault system. You've got San Luis Obispo here. This is north of LA. Parkfield, Santa Lucia Range. Let's see. We have these predictions based on the history of activity on a fault. They could be problematic because we can't really predict exactly what will happen in the future. We can document past events. We can monitor movements, but we can't say exactly what will happen when, unfortunately. So The San Andreas Fault's Parkfield segment showed a regular interval of about, every 22 years it had a magnitude earthquake of about 6. Um, Geologists, they've measured and monitored the Parkfield segment actively between the years of 1988, say, to 1993, as presented here. It was the predicted earthquake interval of about, 22 years. But in this case, the expected earthquake did not occur until 2004. That was 11 years after the predicted date. We know things are likely to happen, but we can't say exactly when they'll happen. Okay. So, what is the earthquake history of the San Andreas Fault and related faults? You have these segments of recently active faults. That's what these are. This red segment is ruptured that occurred with the 1906 San Francisco earthquake. And what I'll note is that the San Andreas Fault system does have distinct segments. They are mapped here. An earthquake hazard varies along the fault because the segments vary in size and frequency of earthquakes. Okay, so this is our creeping segment as well with the Hayward Fault. The Parkfield segment, the north end of the orange line, ruptures, we'll say every 20 years, but like I said from the previous slide, can't say exactly when. And the last full rupture on this orange segment was 1857. We have moderate earthquakes along this eastern zone as well. And we'll look further at the San Andreas Fault. It has several features that are common to active faults. Believe it or not, you can have ponds, offset drainages, linear ridges, scarps, linear valleys, and drainages that are parallel to the fault, and then little springs with water associated. And we have here a stream channel offset to the right by a fault and an aerial photograph of the same area. So these structures are, like I said, common to active faults. Okay. You can also, as a geologist, look at the subsurface and collect physical samples. This isn't typically something that would be done like right when an earthquake happens. It's part of a long-term study. We can look at this landscape and think about how we could obtain these samples. So we have exposures of deep uplifted rocks that might have been brought to the surface through an earthquake event. Scientists can look at rocks in mines. Of course, those would provide a detailed subsurface view because tunnels have continuous exposures. Sometimes mines can be several kilometers into the subsurface. Let's see. You can drill cores out and look at the rocks here, look for anything that's offset. And then magma can bring up pieces of deeper rocks as well, like that principle where a younger rock can contain pieces of an older rock. So that gives us a picture of the geology in a fault zone. Beyond that, seismic reflection data through a geophysical survey can distinguish the layered nature of the subsurface. And we discussed this a little bit in the seafloor chapter. You can also do what's called an electric survey or resistivity. That shows the capacity of rocks and fluids in them to conduct current, which can help us understand where groundwater exists or does not exist in an area. And then Magnetic surveys show the strength of the magnetic field associated with various rock types, and a gravity survey is going to show the density of various rock types, resulting in a model such as this. All right, so this is more on how seismic waves travel through material. With energy transfer through Earth materials, seismic waves radiate in all directions. When they hit a boundary of, say, different material, a wave is going to either reflect or refract. And a wave is going to refract downwards in slower material. And then a wave refracts to a shallower angle in faster material. Okay, so a rising wave refracts up, passing from faster to slower material. And we could see something like this. So starting off in all directions, the only thing that's going to change it is different types of earth materials where that energy can transfer through the material faster or slower. And it's going to change accordingly. So refraction causes seismic waves to take curved paths through the earth. In this case, we have a seismic wave bending as it travels through the crust and the mantle, refracting. Rocks actually get denser deeper in the earth, so our steeply descending rays will first be refracted to shallower angles as they encounter faster material at depth. We say it's faster at depth. And then waves will bend back toward the surface as they pass through the slower, less dense material. So close to the earthquake, the paths through the crust arrive first, and then farther away, paths through the faster mantle arrive first. And what can we do with that information? These are the ray paths of seismic waves through the earth. So we're just cutting the earth in half here. You have P and S waves going through the earth from an earthquake event. This is the earthquake source. The P waves speed up and down as they travel through the earth depending on the material they're traveling through. And then, of course, faster velocities indicate denser materials, and we get denser materials here. The P waves and the S waves can travel curved paths that return them to the surface as well. What we end up having with that is a shadow where the P waves and the S waves could not travel. And geologists actually use the shadow information to determine the size and the nature of the Earth's core, which is pretty cool. So the size of the core is indicated by the location of the P wave shadow zone. And the S wave shadow zone is here because S waves do not pass through the liquid outer core. Okay. So how do geologists investigate deep processes like deep earthquakes? We must look at rocks with deep origins. So we would document the minerals and structures in rocks that formed under high pressure and temperature conditions to understand what processes and conditions occur deep within the earth. So these are blue schist and eclogite in California from deep within the earth, but they were brought upwards through transfer of energy, really. We can use computer models to sort of get an insight on processes that are too deep within the earth to observe directly. And we can also try to replicate deep earth conditions in the laboratory. Rocks can be subjected to high temperatures and pressures in order to determine the conditions under which they melt, solidify, or flow in a solid state. We can use seismic tomography to explore the Earth's interior. That allows scientists to examine earthquake waves as they pass through the same subsurface region, but from a different direction. So we've got seismic observations from different directions. All right, so ray paths coming from points A and B are recorded. And then higher seismic velocity, it means a wave will arrive at a recorder sooner than expected, right, through denser materials. And then slow regions means that the waves will arrive later than expected. And in this way, we can figure out where different Earth materials exist in the subsurface that we couldn't see otherwise. It's all about how fast these waves can travel through the subsurface. Okay. So seismic velocities of the lowermost mantle vary from place to place. In this case, the velocities of red would be slow. Blue would be faster. So a seismic wave quality or characteristic could be a shear wave velocity, and that can be used to distinguish parts of the lower mantle. And the red and the blue areas, of course, are interpreted to have different seismic velocities. The red zones transmit seismic waves relatively slowly. The blue zones are relatively fast. Some geologists think that the blue zones are subducted plates. If I can just go back to get a look at that. And the red zones are rising plumes, but that's still kind of controversial. There's not all the evidence that everyone wants to agree upon that yet. And this globe is a model that helps visualize these interpretations. You can kind of see the lower mantle here, right? The outer core, the inner core, the core mantle boundary. The subducted oceanic plates are sort of collecting along the core mantle boundary, corresponding to the blue zones. And then the plumes of mantle material rising from large upwellings correspond to the red areas. And that's why some people think that the blue zones are subducted plates and the red zones are rising plumes. And with that, we'll stop here for this chapter.